thanks very much for having me as part of the CLF today. I'm going to be talking mostly about enclosure retrofits and embodied carbon. It's going to be a fairly high-level talk over the next maybe 15 to 20 minutes. It's lacking a little bit of hard data, so because it was a bit tough to figure out sort of project-specific examples, but certainly something worth chatting about afterwards if you feel like reaching out and connecting. Embodied carbon is nothing new. We just are thinking more about it for myself in the context of existing buildings. You know, we could talk a lot here about local resources, local materials, but the durability is pretty key. This is a mountain hut in the French Alps. For wayward hikers who may find themselves in a bit of a squall, clearly doing a very good job of its design intent for quite a long period of time. So I think a lot in the same way about existing buildings and how we can repurpose them to both enhance their functional performance as well as extend their service life. Just setting the groundwork a little bit for the embodied carbon discussion. I know that this is maybe a little bit basic for most of the team, but just wanting to sort of set the groundwork that we have spent so much time, certainly in the last 10 to 15 years, focusing on building operations. And I recall early in my career, sort of in the sustainability world of 2007 and 8, where embodied carbon was discussed, but in the context of how much buildings consumed from an operational carbon perspective or emitted from an operational carbon perspective, it was a relatively small proportion. But as we push for higher and higher performing buildings that are lower and lower carbon operations, embodied carbon becomes a much more substantial piece of the pie. And so we need to pay more attention to it. I'm just going to skip through a lot of this because everyone in the forum is very aware of embodied carbon, but I will be focusing mostly on the replacement, repair, maintenance use, this kind of B section. Maybe a little bit about the C, but really kind of honing in on that existing building reuse. As I mentioned, in a net zero carbon world, embodied carbon is 100% of a building's emissions. And so it is very important that we focus on it. I'm going to also just reinforce that time is of the essence, and upfront embodied carbon emissions represent the largest proportion of carbon emissions for new buildings for a substantial amount of time. So this is a slide from assuming 2020 as day one, where 100% of the carbon emissions from a building are embodied. Even within 10 to 15 years, embodied carbon is still the majority of emissions. Some of you may have seen this series of graphs. I want to talk a little bit about retrofits of existing buildings and how we need to change this trajectory. So what does this graph mean? It's a simplified graph of a building project we were looking at, where we knew the embodied carbon on day one of 5,000 tons of CO2 equivalent. You see there where that graph starts. Every year of operation, it is emitting a certain amount of carbon emissions. And so over the life of this building, in 100 years, it will have emitted a total of, north of 35,000 tons of CO2 equivalent, and 5,000 of which came from its initial embodied carbon. So in our world where we know that existing buildings are the key to to addressing the climate crisis, we have to be mindful of what we do at that kind of opportunistic or that midlife intervention for existing buildings. The problem is that often what we do is we retrofit and we use a like for similar approach, which unfortunately over the next 50 years doesn't change the trajectory of the carbon emissions. And at the end of the building's life in another 50 years, so at 100 years, the total carbon emissions are just higher. So now close to 40,000. So I want to encourage folks to think differently about existing buildings, to think about changing the slope of this graph. and looking at more efficient retrofits. And those efficient retrofits certainly have to do with HVAC systems. But as an enclosure specialist, someone who focuses really on the demand side, we also know that some of the best low carbon M&E systems are enabled by supportive enclosures, which provide thermally efficient, airtight, and good solar heat gain control. So the intervention, and we also know that these kind of enclosure retrofits that we're talking about that provide an opportunity for significant upgrades really only come along every 20 to 40 years in some cases. So there is an opportunity that must be taken at that stage to change the slope of this graph. There's even I think a greater opportunity. So just scrolling through, looking at the avoided emissions. I'll throw out, if you're a fan of Good to Great, the big, hairy, audacious goal would be to look at perhaps a low embodied carbon retrofit, as well as a carbon positive retrofit, which potentially results in a very significant drop in avoided emissions. But if you look at the slope of this graph, the end of this graph after 100 years is lower than it was at the 50-year intervention point. So in effect, this building has become a climate positive building and is technically kind of negating past operational emissions, say for the last maybe 10 years of its operation. So again, just kind of a big idea of looking at ways to reimagine existing buildings as climate positive contributors. We know also from an embodied carbon perspective that the best approach is to reuse existing buildings. And so we focus a lot on this kind of the top 80 to 100%, which is either build nothing or build less. But in fact, what we need to do, as those lines suggest, is bring a lot of our current knowledge, low carbon materials, minimal resource consumption, more efficient mechanical electrical systems, lower energy, lower exergy, into those existing buildings. And a good retrofit with a supportive enclosure is what enables that. And lastly, as I start to conclude, I want to take an example from a residential mid-rise building, and just conceive of the opportunity that we're talking about. So in a new design scenario, our exterior enclosure might comprise this chunk of embodied carbon. I apologize if it's a little bit busy, but as Sankey diagrams tend to be very intuitive in terms of where the embodied carbon impact is coming from. And you can see two different colors. There's sort of a hatching and then a solid color. So the top end of the hatching is the total, I guess, maximum embodied carbon, and then under an achievable scenario or kind of an optimized embodied carbon scenario is the solid graph. So again, on the exterior enclosure side, from a design perspective, we do have obviously significant opportunity to implement low embodied carbon materials, which Kelsey will be talking about shortly. If we talk about existing buildings, we're really talking about this whole stack on this side. And if we kind of highlight the optimal embodied carbon scenario for a new build, even if we were to replicate that in a retrofit, it still pales in comparison to what's currently there with the shell and the substructure. And if we translate that over to the far right, even with the achievable new build scenario, the amount of embodied carbon from retrofit is very, very small. So again, just reinforcing the need to retain existing buildings, to retrofit them, and to optimize their performance and enable these low carbon energy systems. The reality is, unfortunately, that existing building materials sometimes are very hard to recycle, and largely because they're contaminated feedstocks. And this is particularly true in glass. where getting an IGU apart, getting all the sealants off, and recycling probably just the clear light, or downcycling the light with the low E is sort of a best case scenario. Aluminum and concrete and even UPVC, some of these products are a little bit more recyclable with a little bit of contamination, but glass continues to be a big challenge. I also just want to throw out another thought here. With existing building retention, this is an example of typical sort of facadism of retaining an existing facade. I did this sort of 2-photo overlay where you can see the final product was full demolition of the backup structure, but retaining this heritage facade. Chatting with some of my embodied carbon specialist colleagues, and we were just sort of throwing down different ideas of, what are the avoided emissions of the heritage facade versus the new? What about that big steel structure that's supporting that facade? What about the emissions from the demolition and even the window replacement? And I fully acknowledge I'm a heritage specialist as well as a fanatic. So I believe there's a lot of value in this besides just the embodied carbon, but it's worth considering in the context of the larger building. What are we doing with that structure afterwards? Is that getting repurposed or reused somewhere else? Is it being fully recycled and fabricated into a new support structure that's going on to support the next facade retention building or facade retention project? So just thinking more holistically about how we're impacting the embodied carbon equation in the retrofit world. A lot of you will have seen these graphs, so I'll just sort of speed through, but we do know that there is this trend of warming, this is for Toronto, with the projected 2040 scenario being pretty solidly in climate zone 4. But what's not often discussed as frequently, but is very obvious in this set of graphs, is the variance year over year. So if we use the historical energy data or the historical weather data from 1959 to 1989, you can see that there's about a 5 to 10% year over year variance. If we look at that next set of climate data, the 2000 to 2014, it's a 10 to 25% year over year variance. So yes, there is overall warming, which affects heating degree days and heating energy consumption, but there's also an increase in the variability year over year. So that speaks to the ability of the building to switch over from heating to cooling if it's a 2-pipe system, or for it to be more resilient if the power were to go out. And so we do expect that trend will continue in addition to the overall warming trend. Lastly, just a couple of examples. These are a couple of our projects and then one other project that is not ours. 401 Bay Street. So this is an existing building facade replacement where the existing precast and everything was retained on the building, structurally improved, insulated and clad, and then a new window system was put in front. And the old windows were removed from the inside, and the sill was extended while the building was fully occupied. And so this was about a 72% improvement on window U value from the original single glazed windows to the new double glazed curtain wall system. About a 50% improvement in opaque U value, not just spandrel, but opaque, because the original building had precast spandrels, which were insulated, and then curtain wall hung in front of it. And all of the vertical precast elements were also insulated, which you can see in the middle photo with the overcladding. And not insignificant energy savings. And you can see in the bottom right, the tall blue line is the existing enclosure heating demand, and then the little light blue bar is the post retrofit heating demand bar. Another example for the folks here in Toronto, 120 and 130 Adelaide. These are two buildings, two fully occupied commercial office buildings, which were also fully retrofitted. The entire structure was retained. The entire curtain wall framing system was retained. we just replaced all the IGUs and replaced all the metal spandrel panels in front with a pre-glazed cassette system that's secured directly to the existing curtain wall structure. So relatively low embodied carbon intervention, which resulted in significant improvements on both vision U value and spandrel U value. And importantly, in these commercial buildings that are cooling dominated, a reduction in solar heat gain, which helps to reduce occupant comfort issues with overheating, as well as total cooling. We did look at the heating energy implications, and with this U value improvement on the vision and spandrel, it was relatively even. So yes, we were getting a little bit less free heat in the wintertime, but the improved U value kind of helped to offset that. And there's also a big air tightness improvement benefit with these kinds of retrofits. Turning to the residential side of things, this is an existing residential building that had a window wall system that was aging and needed significant replacement or repair. Rather than replacing, we designed a retrofit solution that retained all of the existing window wall. And importantly, I don't know if it's easy to see here. Don't know if I can do a markup, but hopefully you can see my, oh, here we go, a laser pointer. The simple single glaze bypass sliders were replaced with awning. And then more importantly, the slab edge, exposed slab edge, was overclad with insulation and new metal panels. So all of the deteriorated metal panels were taken off. Any backup conditions that were air leaky and water leaky were repaired, and then a new metal cladding and insulation was put over the front face to both insulate the mullions and insulate the slab edge to significantly improve overall thermal performance for the enclosure. And then we're getting into a lot of deep energy retrofits, in some cases zero carbon retrofits, a lot of multi-unit residential buildings, and primarily in the public housing sector. This is an example of overcladding, new windows, new doors, some renewable energy on site, looking at a 70% TEDI reduction. So very significant improvements to both resilience, comfort, and overall performance for this particular building. Keeping in mind, as the second bullet says, ventilation upgrades are critical for these buildings to remain habitable, comfortable, and healthy to be in. And then one example, which probably a lot of people are familiar with, the Empire State Building, unfortunately not my project, but these were existing windows that were reused, which was kind of interesting. And I don't have a ton of information. You can find out more on this this particular web link. But yeah, 96% of the window materials were reused with significant improvements in the glazing U value. So again, a very significant heritage building. The windows, even though there's probably very little insulation in the walls to begin with, they're still better performing than most windows. So improving the windows does result in a fairly substantial improvement. So that's the end of my my section. I think I'm going to pass this over to Kelsey now, and she can carry on.
Great, thanks, Scott. Get my screen. Okay, everyone's able to see my screen?
Yeah, we're good.
Okay, thanks, Scott. Okay, so Scott talked about existing buildings. I'm going to be talking more on the new construction side and looking at, so I'm involved in a research project funded by the Atmospheric Fund, and we're kind of co-researching with Toronto Metropolitan University, formerly Ryerson University. So I'm going to run through kind of where we're at with that study. Unfortunately, we're not complete, so we don't have a ton of outcome data yet, but that is coming soon in the next couple of months, so I'll keep you posted. I'm going to go through a brief introduction, talk about why we decided to focus on building enclosures for our study, discuss a couple of examples that have guided how we've approached this study on whole building embodied carbon, rather than just our focus on the building enclosures, and then give a quick overview of the current study and where things are at. So Scott already went through a lot of this. I just kind of wanted to set the stage. So this is an example of a whole service life of a building, the operational unembodied carbon emissions over an 80-year service life. And this is a building built to code minimum. So the split, as Scott mentioned, this is kind of not really buildings that are built today, or buildings that are built to code minimum today. This is a pretty long service life. So we have a lot more operational, but 80% operational carbon, 21%, but 20% embodied carbon. And so we have a kind of large chunk of upfront carbon in 2023, say the building's built next year, and then the yellow bars being operational. And then there's also maintenance and repair in there, which is the orange chunks as we go through the decades. So if we go from building to code minimum, optimizing for low operating energy with kind of good building design, good performing enclosure, then we can reduce the operating energy pretty substantially. And if we take this a little bit further, say we go for low energy building, but also not using any fossil fuels, or go through for Ontario, this would be like electrification, we can further reduce that operational carbon emissions. That split gets us to about that 50-50 of embodied to operational over this 80-year service life. But the problem is, like as Scott mentioned, we only have a short period of time to really make significant change. We don't have until 2100. We need to do it now. And so if we look at this closer from now to 2050, this split becomes more of an 80-20 in favor of embodied carbon. So looking at those embodied carbon emissions now is really crucial, both for existing buildings and for new construction projects. And so why, in this context, why did we choose to focus on building enclosures in particular for our study? Well, there's a couple reasons for this. One, if we look at this orange bar and break it out in terms of, this is kind of A1 to A5 in those categories. I'll describe a little bit about that later, but I'm sure you're mostly familiar with that. So we have the production of the materials, which is A1 to A3, A4 being transportation to site, and A5 being construction stage activities. You can see the biggest chunk is that A1 to A3 production of materials. And in this, we can break that down even further into what elements are from the walls, the roofs, other materials, foundations, floors, and beams and columns. So the yellow bar, or the components in the yellow bar, that's the building enclosure. And then we have in the gray, that's your building structure. So we already know that the structure is a significant portion of our upfront carbon emissions. We hear about that a lot. We hear about the importance of concrete and low carbon concrete in the design of low carbon buildings. But the building enclosure is also a significant chunk. It does depend on the configuration of the building, the size of the building, but the building enclosure can be, upwards of 50% of the whole upfront carbon emissions of the building. Another reason being that RDH specializes in building enclosure design and building enclosure consulting. So that's another reason why we chose to focus on the enclosure. We're not structural designers, so we decided to kind of leave that for somebody with more expertise in that area. Building enclosures are our environmental separators. So our choices in designing our enclosures, the materials we select, both affect operating and embodied emissions, and they affect the enclosure's long-term performance, as well as the building's long-term performance, and the durability will impact the overall embodied carbon, because it will impact that maintenance and repair sequence as well, and how much carbon emissions are involved in that maintenance and repair piece. But building enclosure emissions are also very complex. Obviously, there's a lot of material choices out there for every single piece of an enclosure, whether we're talking about the structure, the insulation, the sheathing, the membranes, the cladding. There's so many choices. And there's a lot of different reasons why you may choose one or the other, whether you're the designer, the client, the consultant. And so there's a great amount of variation between building enclosure assembly options. Of course, we had to limit this when we were looking at our study to a reasonable set of representative assemblies. I'll talk about our decision-making in that process as well. So a couple of whole life carbon benchmarking studies that were also funded by the Atmospheric Fund that are now both complete. I just wanted to touch on those. You may already be familiar with them. I know that you've probably had a couple of these presenters at the Carbon Leadership Forum presentations in the past. But this first one, this is a Part 9 study of emissions of materials benchmark for residential construction. This was done by Builders for Climate Action and Passive Buildings Canada. The most recent study is the bar at the bottom. Builders for Climate Action had done some previous studies, one for NRCan and one in BC. And then most recently, they did a study of 500 homes in the GTHA. And the purpose of the study was to benchmark, what is a worst case scenario whole building embodied carbon for a house? What's an average and what's a best case scenario based on the homes that are out there today? So no intervention done, no assessment done yet at this point, but just what exists in their study of 500 homes, and that's single family, semis, and townhomes. And so this provides a good, useful tool of kind of where, if you were to calculate the embodied carbon of your building, where do you sit in this best, average, or worst case scenario? City of Toronto, Mantle Developments, and the University of Toronto did a Part 3 study that's recently been completed as well. So they did an industry survey, had consultants, architects, developers provide data from LCAs that they had done on projects. Of course, there's a lot of variation in the methodology that was used and in kind of the A1 to D, like what categories of embodied carbon were used. But they had a response of, they were able to get kind of 2 multi-unit buildings below 4 stories, 13 above 5 stories, some commercial office, and some other building types. So presumably that would be like our institutional buildings and other building typologies. So in this study, they were also able to provide a kind of average benchmark in this kind of 400 kilogram CO2e per square meter of floor area. And in this study, the kind of, I think that an interesting piece of this is they also, because of the way that they categorize the data, they were able to see that with all of the information collected, that upfront carbon in this A1 to A5 category that I've previously talked about 90% of the emissions occur here if we look at the full A to C of embodied carbon. And so if we dig down to this a little bit further, this A1 to A3 production stage, just the production of the materials that are used, that's actually 84%, so a very big chunk. So in our study, we ultimately decided to go A1 to A3 because we're not site specific. Our study is looking at the GTHA as a whole. So now I'll go through an overview of our embodied carbon metrics and guidance for building enclosure design. Again, this is collaboration between ourselves and Toronto Metropolitan University and funded by TAP. Our objective here was to establish an industry and municipality accepted methodology for calculating the embodied carbon of building enclosure assemblies. We did consult with the City of Toronto for this. The intent was, we want to make sure that we're developing a tool and a product that is going to be useful for when the City of Toronto does integrate embodied carbon benchmarking into their Toronto Green Standard, or any municipality that provides, even the zero carbon building standard, that provides a benchmark target that has to be met, which the City of Toronto actually did do this year. So we wanted a tool that they would get behind, that was going to be useful, that designers can use to calculate that early stage embodied carbon of their buildings. And then the second objective was to provide support to design teams in order to be able to provide that data, and also to be able to make early stage decisions on building enclosure design to reduce whole life carbon before they get to those later stages of costing, when it's a lot more difficult to make those changes. So this is I'm sure you've seen this table before. It just talks about the various stages in the whole building life cycle. All of the blue highlighted areas are those that are related to embodied carbon, A1 to A5, and the dark blue being the most emissions occurring there. And again, we focused on A1 to A3. Where does our embodied carbon data come from? You may know there's a lot of information out there, a lot of EPDs available, but it is limited if you're trying to be location specific. So if we're just looking at the GTHA, it's a bit of a challenge. You can find generic and proprietary data on various inventories. So we have the inventory of carbon and energy, the ICE, programs like Athena, which is really commonly used across Canada, and one-click LCA, which is ultimately what our team decided to use for our assessment. Also the BEAM estimator, the BEAM tool that was developed by the Builders for Climate Action. There's also spreadsheets, so NRCan has a spreadsheet, the MCE2, and then in-house collections. So like RDH, for example, we have our own in-house collections of materials, and I'm sure many other consultant organizations that do LCAs do as well. Also EPDs, so there's industry-wide coverage with averaged data. That is what we tried to use, this more generic industry-wide average data for our study before we start to bring in manufacturer-specific information, because we didn't want to favor one manufacturer over another. We're essentially manufacturer agnostic, but it's really about, you know, what does it take or what does it cost from a carbon perspective to create a metal panel cladding, and trying to use an industry-wide average for that. Of course, it's always important to use the latest data and information. This is constantly evolving industry and a moving target. So this is a bit of an iterative process as we go through this study that will be ending in the spring in terms of what information we're using for our final calculations. The process was as follows. So we first defined what assemblies. We have 25 assemblies overall. We have a mix of wall assemblies predominantly, as well as roofs, floors, and existing and new construction, just a few existing assemblies, existing building assemblies. And then we collected our embodied carbon data, again, in that A1 to A3. We used one-click for this with some values provided by product-specific EPDs if there was no generic data available. Which was the case in some instances. We then did material takeoffs to collect a volume or weight for each of the materials based on a 9 square meter wall assembly, and then calculated the embodied carbon for each. We reviewed the results. We now we're at the point where we're almost finished conducting the calculation for all of the assemblies and evaluating the results for a report that's due mid-December. Unfortunately, we haven't yet. The most important for me, the one I'm most interested in seeing, is conducting this sensitivity analysis of what are the key drivers of embodied carbon in building enclosure assemblies. Like, what can we tell to designers tomorrow to say, if you're going to focus on one thing to get a more low carbon building, this is what you should focus on. Or, you know, cladding attachment, don't worry about calculating that because it's not a significant chunk. So these are the things we're trying to figure out, and that analysis has not yet been completed. We then, of course, iterate the process, go back to defining the assemblies. We've kind of gone through this process already, and then create a guidance document to inform early stage decision making, and that's ultimately the goal. And then we'll be disseminating that. We looked only at GTHA specific assemblies and materials based on RDH experience. For Part 3 buildings only, typically in the institutional residential range, and we did do new construction and existing building retrofit assemblies. We also had to set performance targets. I don't have time to get into this in too much detail, but essentially we looked at the Toronto Green Standard version 4, tiers 1 to 3, because we're in version 4 now. I know some buildings are still going through with version 3, but we're in version 4. So we want this to be not become obsolete after a year. We want this to be useful for the next 4 years. So we're looking at version 4, tiers 1 to 3, which is essentially the old tiers 2 to 4. And we developed our enclosure performance targets based on this. So I can't get into kind of how, but we did factor in thermal bridging into this calculation. So if these are our whole wall targets, say for tier 2, we have a roof of R20 or a wall of R10. This is for a high-rise MERB example. We did have to include some thermal bridging factored into there to get for a clear wall R value. So rather than R20, we're R25 for our clear wall, so that we account for some thermal bridging. Roofs are R30, glazing thermal performance U 0.22. We're doing a separate study around glazing that I don't have time to get into today. And then window to wall ratio is just, we're not factoring in window to wall ratio. We're just breaking the window down into its elemental parts. This is our full list of above grade wall assemblies. We have about 13 at this point. These are only the new construction ones. Again, there's so much variation. We just wanted to capture some typical assemblies that we've seen on a variety of different building typologies that are within the realm of this study. And so we looked at exterior insulated CMU with brick. This is like a common institutional assembly for new construction. Some split insulated assemblies. So one with just exterior insulation metal panel, one with EIFS, with EPS. We also looked at some wood-based assemblies for that kind of low end of the mid-rise. And so that would be either wood stick-built or CLT. We're seeing a lot more panelized CLT construction, especially with these more low carbon targets. Double wide insulated precast. So there's kind of two different options here. One is a phenolic foam. It has much higher R per inch. So we wanted to look at, because there's less of it, what is the impact on embodied carbon? Whereas if you do XPS, to get to that R25 target, you need more. And all of these have been calculated to get to that R25 target. So that's where that variability comes. And we wanted to evaluate the impact of different insulation types based on their R value per inch. We also looked at insulated window walls, spandrels, both with mineral wool and spray foam, two kind of common approaches to that installation. Insulated metal panel, commonly used for mechanical penthouse situations, but also potentially sometimes for zero lot line conditions. And architectural precast, again, both a spray foam and a mineral wool approach. We calculated the effective R value, as I mentioned, to get to that R25 target. Of course, they're not all exactly going to hit R25 because we wanted to be realistic about the thicknesses of material that we were using. We also, within that R25, did factor in some thermal loss or thermal degradation based on the cladding attachment system. So for example, in this W01, here you can see all of the layers and the effective R value in this column here. The thermal degradation is in this far column. We've said about 10% loss for stainless steel brick ties. It's a pretty conservative estimate. So we are factoring in, and we will be listing all of our assumptions, but we are factoring in, we think it's important to factor in cladding attachment as well. In the W02, as a similar example, in this case, we have intermittent clip. So I guess we could say it's a fiberglass clip, but it could also be stainless steel. We're basically just saying 25% thermal degradation, which is kind of in the average for an intermittent clip system. It can be a bit higher, it can be a bit lower. 25% thermal loss. And again, these values are 25.7 and 24.8. So we do have to kind of average it out. Finally, the global warming potential. This is our upfront carbon. We've calculated per square meter, and then we're identifying the materials that are the most substantial. So that would be, in this case, it's the CMU, it's the mineral wool, and it's the clay brick, which isn't surprising. And they're pretty significant. We've identified the percentage of the overall, 38% and 33%, 20%. And then the embodied carbon per square meter. The idea is you could take this number and multiply by the surface area of this assembly, do that for all of your assemblies, and then get a really rough early stage whole enclosure embodied carbon number that then you can start to tweak by changing your assemblies. We also included, this is I think I have one more slide, all of the environmental impacts to see, what are the most substantial or what are some of the other environmental impacts so that we can compare assemblies together. So we have global warming, acidification, eutrophication, ozone depletion, and fossil fuel primary and formation of tropospheric ozone. And in these, we also identified which are part of A1 to A3, and you can see most of these are in the kind of 65 to 85% A1 to A3, which is, again, just kind of validates that selection of A1 to A3 category. The outcome is a 1 to 2 pager summary of our results to be posted online in an open source database available to everybody, to then create a guidance document based on the sensitivity analysis to help inform early stage decision-making around embodied carbon in building enclosures, and then disseminate through workshops for the industry. And that's it.
Awesome. Thanks, Kelsey. Huge thank you to you and Scott for presenting today. So we have about 15 minutes, so we'd like to open it up to questions from the attendees. So if you have a question, you can raise your virtual hand and then, or type it in the chat. But if you'd like to speak to the presenters directly, please feel free to raise your hand and we can do that. I didn't see anything come in during the presentations. Looks like we got one right now from Rami. So for assemblies that include masonry, are the embodied emissions from the mortar and grout being accounted for? I believe that's for you, Kelsey, regarding your studies.
Yeah, that's a good question. Yes, they are.
Great. So I can, I have a question myself actually, so maybe I'll start the conversation. We can see what else comes in. But yeah, I just wanted to hear from both Scott and Kelsey. What, if anything, are you seeing from manufacturers of building envelope components around upfront carbon and reducing that impact?
Okay, I can start. So we're starting to industry's becoming more wise, obviously, with this. So we're starting to see a little bit more. It's still in its infancy, I would say. It just in terms of the reaction, they're not really being asked to do much. So they're aware, but they're not really doing that much. Obviously, I mean, we've seen the kind of switch from HFC to HFO in the spray foam industry, so that's pretty huge. That's a response to this. I mean, all environmental impacts, but also global warming potential, of course. So I would say that's a big one. Yeah, I don't know, Scott, if you have anything else, but that's.
Yeah, I agree. I mean, it's still feels very early, or challenge being that there aren't a ton of options and proven examples of low embodied carbon materials also in large buildings is tougher to find. So we're not, I mean, we're a little bit I'm a little bit risk averse, but at the same time, don't want to just obviously shut the door because there's no, building that's had it in the walls for 40 years to prove that it's fine.
Yeah, and one thing we're getting through this study, we did have a workshop back in, I think, May of this year, and we talked to some. There are only a few manufacturers there. We talked to some local manufacturers of products, and basically they said there's no incentive for them right now to be even providing EPDs, let alone trying to then use that information to reduce their overall embodied emissions, just because if they're doing it, they're paying out of pocket. They're not being asked to do it, so it's just a cost to them, and nobody else is doing it. So that's a bit of a limitation right now.
Awesome, thanks. All right, we have a raised hand from Charles.
Hey, Michael, thank you. Fantastic event, and Kelsey and Scott, thank you for two exceptional presentations. And I'd just like to ask you, your presentations make it clear that in your respective practices, you're working on really great projects and doing great research and developing fantastic insights. I would love to just hear, as it relates to a design process for existing building or new construction. I know in our practice, we're trying to identify the right frameworks and approaches for evaluating whole building life cycle carbon and making real-time design decisions that are optimizing across, do we add that extra inch of insulation? Do we pursue triple glazing, right? Do we go mass timber and so on? Particularly in the enclosure where the thermal, the embodied carbon, the energy modeling are all totally integrated, and trying to find how to make those decisions. So given the advanced work that you're both doing, I would just love to hear, how are you finding that process emerging of making the best decisions, and how are you making observations on balancing all these important factors in a fast-moving landscape?
I'll share some of our own. Thanks, Charles, for the question. some of our own practice. We have some tool development, as most people are wont to do, that looks at the thermal performance of the enclosure, the impacts on energy consumption, and the embodied carbon, all in a parametric environment. And so again, that's going to be deployed, project specific, where we get the scope and fee to do that kind of work. We're doing a little bit internally for our own practice, just to build our own knowledge and capabilities and our expertise in that area. But it is at its infancy, and it, the tool is not something, it's not like Frame Plus Online that we provide for everyone, where you can just go and plug in your numbers and away you go. But ideally, in the future, it'll be a real-time design tool that we can use. I'd say we're probably not super far off from that goal, but that's kind of where we're at.
Yeah, and I would say kind of this in the same vein. The reason why we embarked on this study is because we feel like we're lacking information on being able to do this early stage analysis, and like getting a lot of questions in those early stages of design from design teams on, what about this versus this? And because it's such a balance between that operational, their energy targets, and the enclosure design and what the implications are for embodied, that's really what sparked this study. And also in that sensitivity analysis, that long-awaited sensitivity analysis is going to tell us, what are the key levers. So I think we're still, we do some, when we get questions around like cladding, for example, we'll provide information on, where the various claddings sit in an array, if we can get that information from the manufacturers that are being looked at. But really from like a whole holistic viewpoint, it's still pretty limited in what we're able to do because we just don't have the information.
Great answers. Thank you both.
I'll also mention that our tool is named Greta in honor of Greta Thunberg. So
very apt.
Yes.
All right. Thanks for the question, Charles. I'll take two quick questions from the chat and then move on to David, who has his hand up. So question for Kelsey, any information on when the data from your study will be available to the public?
Yes, so definitely by the spring. Do I know? I don't know if anything will become publicly available prior to our kind of final TAF completion date. So I know that that's the spring of this year. Let's call it April. But before that, will there be some preliminary information provided? I can't really say. We might do that just to promote the study, or another session like this, somewhere where we kind of talk about preliminary results. But I think publicly and published data will be this spring.
Awesome. Another quick question for Kelsey. In the assemblies, are sealants and caulking also included within the embodied carbon calculations?
No, sealants and caulking aren't included. That's an interesting question. So we have a list of like a bucket list of things that have come up throughout this study that we want to look at. And, sealants would be one of those for sure. So I'll put it on the list, but because of the limited kind of scope and breadth of our study, there's only so much we can do. So it's a really good question.
All right, I'll hand it over to David, who has his hand up.
Yeah, thanks for that. So it actually kind of relates to Charles's question. The notion of trade-offs, starting to see some preliminary analysis that suggests in jurisdictions with clean electricity grids like Ontario, that it actually, from a carbon point of view, doesn't necessarily always make sense to go from double to triple glazed windows, because there's a more embodied carbon content, and the fuel switching is the sort of the better way to reduce carbon overall, which kind of aligns with what we're seeing in terms of industry trends, which is fuel switching before investing in the truly high performance envelope. So I'm curious to hear your thoughts on that, and what this might mean for both new builds and retrofits, where the envelope tends to be the more expensive investment versus fuel switching. Just curious if you want to comment on that.
Yeah, I can start. I'm very interested in this topic of we've talked so much about getting to a place where every building is like passive house certified or, net zero carbon, or meeting these really stringent targets with really highly insulated enclosure systems. Not that insulation is the only driver of embodied carbon, but it is one. Or like you said, triple glaze versus double glaze. Does getting to that level of performance make sense? Because there's actually quite a bit of a cost from a carbon perspective up front to use those materials in the building. I don't know the answer. I know the study you're referring to, Kelly Doran has been working on this. Yeah, it's a good question. It's part of the answer that we're hoping to get out of this study, maybe as a next step, which would be, now that we have this information available, can we start to do some of these early stage analyses in partnership with a block energy model at the early stages of design to figure out where that balance lies. But we haven't really had the opportunity to do much of that yet.
Yeah, no, fair enough. Thanks, Kelsey.
Yeah, I'll add to that. We've done a little bit of study with different insulating materials and what the impact is on energy and how that then translates to total building carbon emissions. But yeah, it's interesting some of these comments, which are really pushing, and I very much so in the name of this group of the Carbon Leadership Forum, just challenging even where we are today. And I'll share a quick thought about air tightness testing as an example. We helped with the City of Toronto's guidance document on air tightness testing for buildings 2 or 3 years ago, and already people are saying, oh, it's not stringent enough, or why aren't you using this metric? Why aren't you? And it's like the industry is just changing so fast. So yeah, I encourage everyone on the call to just keep pushing for better data, for more innovation, for us to really comprehend and capture this information properly. So good on you guys for all you folks, I should say, for the carbon leadership aspect of this group. It's really encouraging.
Awesome. Thanks both. All right. I don't believe we'll get through all the questions that came in, so I just put in the chat our email. So if there's any unanswered questions that you'd like answered, please send those to info@clftoronto.com. I do think we still have time for maybe 1 or 2. So I'm attempting to go in order from chat in hand. So I'll go to chat now. Question from Randy, and Randy, feel free to unmute if you'd like as well. But the question is, waste rates for enclosure components are 5 to 18%. And will that be ignored if you're leaving category A5 out? So that's for you, Kelsey, on your study. There's another part to that question, but maybe we'll start there.
Yeah, I'm on. So okay. Yeah, with enclosure, it's a little bit different than structure, right? Because you have higher wasted rates, you have IGUs being replaced. There's some products out there that we're ignoring A4, where maybe we shouldn't be, like wood fiber insulation imports, for instance. So by using only A1 to A3, are we, is that a good idea for enclosure stuff? I kind of, put up the question.
Yeah, it's a good question, Randy. We ultimately decided to do that. We started with A1 to A5, and then we ultimately decided to just focus on A1 to A3 because we don't have a project site. We're trying to make this as kind of widely usable as possible broadly to the industry, and to just kind of get some information out there that's useful to do some of this early stage decision making. So it's a good question. We did a lot of back and forth. Ultimately, we decided A1 to A3, but I'm interested to hear more of your thoughts on that.
We should have a beer sometime.
For sure.
All right, we're at 1 o'clock now, so apologies to anyone whose questions we couldn't cover today. Again, please send them to info@clftoronto.com. But thanks again, everyone, for joining today. Huge thank you to Kelsey and Scott as well for presenting, and we will be posting a recording of this session on our website. So have a great day, everyone.
Thanks.
Thanks, guys.
Thanks, Michael. Thanks, Alistair. Bye now.
Thank you.